Good morning, everyone. My name is Gunhan Gulsoy, and today I'm going to present you our work on querying biological network databases with Dr. Kahveci. First, before going right into our problem, I just want to talk a little bit about pairwise network alignment. As Bonnie Berger stated yesterday on her keynote speech, pairwise network alignment tries to find a one-to-one mapping between the nodes of two networks. There are two variations of this problem. One is global network alignment and the second is local network alignment. However, both of these problems are quite difficult. One GI complete and one NP complete. And to give you an example, we tried to align a 50-node gene regulator network with a 7-node gene regulator network using a dynamic programming alignment method QNet, and for a single pair of networks, it took over 10 minutes to complete the alignment. And this being the problem with pairwise network alignment, for our problem, it really adds up to a new level. For our problem, we have a database of biological networks, and then we also have a query which is also a biological network, and we want to do a similarity search in this database of biological networks to this query network. Obviously, since pairwise network alignment is such a difficult problem, doing a one-to-one alignment of all the database networks to this query takes a lot of time. For example, in our experiments, we had a 300 network database, so it took over 2 days to process a single query. Our aim in this study is to reduce the processing time for such queries. There are some existing work on this topic. We can group them in two main titles, one being feature-based indexing, one being tree-based indexing. I will not go into detail about these right now, and about our solution, we can put it into a third new topic, which is reference-based indexing. So here is the outline for the remainder of my talk. So let me start with reference-based indexing, then I'll go into detail about our application of this method on biological network databases. To first explain how reference-based indexing works, I want to use a simpler example, which is not networks but points in two-dimensional space. So here we have DI, which is a point in our two-dimensional space, and we also have a reference point, and we know everything about these 2 points, the distance between them and everything. Also, in this context, let's the distance between 2 points be the similarity between them. So when we are given a query, we want to know the distance between the query point and the database point. But before calculating the distance between these two, we can use the distance between query and the reference points to make some estimations about the distance we actually want to know. What are these estimations? It cannot be smaller than this lower bound, and it cannot be higher than the upper bound, as you see on this slide. So we can make these estimations, but we can further improve these estimations by using multiple references. How do we do that? So you see another database point here in this slide, and using one reference, we can calculate a lower bound and an upper bound for the similarity score. And using another reference point, we can calculate another set of lower and upper bounds, and like this we can improve, or in the worst case, our bounds stay the same, but mostly this interval for the similarity score will shrink. And using more and more references, we can shrink this interval so much that we might end up with very close or even equal lower and upper bounds, such that we might save the time to calculate the distance between DI and Q. So How do we apply this to reference base to our problem, network queries? So here is our database D, which consists of hundreds of biological networks, and you see our set of references here, which are all biological networks, and the size of this set is just limited to tens of networks. When we are given a query, we go over all the database networks one by one, just like we did for the two-dimensional space case, and we calculate a lower bound and an upper bound for the similarity score between D1 and Q. And then we compare these bounds with the similarity cutoff we are given with the query. So, as you see in this slide, if we end up with a case such that the lower bound is greater than the similarity cutoff, we definitely know that D1 is one of the networks we are searching for with this query. So without any further calculations, we can say we add D1 to our result set and return it as a part of our query results. When going over the remaining database networks, we might end up with such a case that where the upper bound for the similarity score is smaller than the similarity cutoff. So this means that we can forget about this network for this query. So we put such networks in our filter set and don't touch them at all anymore. And the third case for a database network might be the similarity cutoff falls between the lower bound and an upper bound. So what happens in this case? We cannot say anything for sure about this database network should be in our result set or its filter or the filter set. So we need to calculate the exact similarity between Q and D3. So we put such networks in our twilight zone, and the size of our twilight zone, as we need to calculate the similarity between Q and query and all of these networks, this size of this set creates the bulk of our running time. So in the metric space, everything was easy. Calculating lower bounds and upper bounds was just the means of triangle inequality. But how do we do these in our network, in network queries, biological networks? So there are two important questions to answer before we can apply reference-based indexing to these. How do we create the set of references, and how do we calculate the lower and upper bounds I just used? So let me start answering these questions right away in the next section of my presentation. First, I'll show you how we calculate the lower bound for the similarity score. So in this slide you see the query and the database network we are trying to calculate the lower bound for. And also we have a reference network which we will use for the calculation. As I shown you earlier, we know the alignments, we know the similarities between the query and the reference and the database network. So using these alignments, we are going to calculate an indirect alignment between Q and D. So how are we going to do this? As you see, Q1 is aligned to R1 and R1 is aligned to D1. So we are going to match these two together. And likewise, we are going to match Q4 with D5, and also we are going to match Q3 with D6. And then after we go over all the nodes, we add the necessary insertion and deletion penalties, and the score of this alignment will be our lower bound for the optimal alignment score. So in order to calculate this lower bound, we just used one reference, but we are using multiple references in our method. How do we use them? So using each reference, we can calculate one lower bound, and just like we did for the metric space, in the metric space, we pick the largest or the best lower bound for our further calculations. So this is how we calculate the lower bounds. Then how do we calculate the upper bound? Let me first point out that using our references, we could not come up with an exact upper bound. In very small number of cases, this upper bound fails. Sometimes it does not even affect our method, but there are some cases that affect our method, and later, as I show you our experiments, we are going to use it as a performance measure for our method. So, for upper bound calculation, we have our query network here, our database network, and here in the bottom, you see the list of query and the database network nodes. And in the first phase of upper bound calculation, we are going to construct a bipartite graph between the nodes of query and the nodes of database network. So, how do we do this? Just like we did for the lower bound calculation, we are going to calculate the indirect alignment between Q and D. Then we are going to add all the indirectly matched nodes to our bipartite graph. We will do this for all the references we have, and we will add any indirectly matched nodes we still do not have in our bipartite graph. In the end, there might be some nodes such as D5 here, which our references do not bring us any information about. But we are trying to calculate an upper bound, and we need to be generous, so we mark D5 that we match D5 with all of the nodes in the query. So this is the bipartite graph we need to construct, and the upper bound we want to calculate is the result of maximum weighted bipartite matching over this bipartite graph. So that is how we calculate our lower and upper bounds. Let me move to the next section of my presentation to explain how we create the set of references for our method. Before the creation of references, I want to talk about three properties of these references for our method to work as good as possible. So first, we want our reference networks to be small. Why is that? Because as I explained to you earlier, network alignment is an NP subnetwork. Local network alignment is an NP complete problem, and small networks can align much faster than the largest networks. So we want our reference networks to be small. The next property is our references being comprehensive. Let me explain this on the figure right here. As you see, we have a database network, and we have some references here. And as we align our references to our database networks, you see they cover some regions in all database networks. We want our references, after aligning all our references to our database networks, we want our references to cover as much region as possible in all of our database networks, and that means comprehensive in our context. And the third property, which is non-redundancy, let me go back to the figure here. As you see, we have another reference, and when we align it, it might cover a region on the database networks that are already covered by other reference networks. So that means redundancy, and that is undesirable for our references. So in order to ensure these properties, we came up with a two-step reference creation method. Well, the first of these steps is we create a very large set of candidate references. And in the second step, we pick a small subset of this C to use as our final set of references. So let me explain the first step in this procedure. In here, let's assume that we already created 4 candidate references, and we are in the process of creating the 5th one. In order to start creating a candidate reference, we first select a random network from our database. Then we pick a random node from it, and we extract a seed from this network using random walk. We continue the random walk algorithm until we reach the limit for our reference network size. Then when we have the seed, we align this seed with all the earlier candidate references we already created. If there is no redundancy, if there is not any network that are similar to this one, we can safely add it to our candidate reference set. So what happens if this seed is similar to any of these networks? To avoid redundancy, we just discard such networks and start creating a new one. So this is how we create our candidate references, and let me explain how we pick a small subset of it. We pick a good subset of C with the help of a set of training queries. These training queries are just possible queries for our database system we are going to put online. And let me just start with explaining picking R. We start with picking a small subset of C, and then we calculate the performance of this reference set using our training queries. What is performance here? As I told you earlier, the running time, the size of the twilight zone, is one of and most important of our performance measures. And the second performance measure in our problem is the accuracy of the upper bound we have. And then in the next step, we try to replace one of these references in R with one of the references in C to increase the performance of R. And we continue this replacement until we reach a local maximum performance. And when we reach a local maximum, that we use that R as our reference set. So this is the overview of our method. Let me present you some of our results and our experimental setup. First, let me explain you our data set. First, we used all the gene regulator networks from key GG pathway database, and we used every networks that are larger than 15 nodes in this database. And as our queries, we extracted 6, 7, and 8 node queries from this database by random walks. And the query selectivity was set such that in each query we selected 2, 4, 8, and 16% of the database. And as our alignment function, we used QNet's algorithm. And we evaluated the methods we mentioned in these results in terms of the running time and the accuracy, the ratio of the true results, and since it's directly affected by the accuracy of our upper bound. So let me show you the first of our results. In this experiment, we wanted to measure how our reference selection strategies change the performance of reference-based indexing. As you see here, I think I'm running out of time, so I'll pick up speed. So as you see here, as we put more effort on picking references, our performance monotonically increases in reference-based indexing. And the next experiment I want to share its results with you is we compared our method with 2 of the existing methods. One is a feature-based indexing method, SAGA, and one is a tree-based indexing method, C3. As you see here, our method outperformed these methods greatly in our experiments, and interestingly, we could not achieve more than 75% accuracy using Saga. And given enough time, C3 achieved higher accuracy values, but it took much more time than our method. So this is all of the results I could share with you today, and I want to wrap up my talk. Thank you all for listening, and I'll be happy to answer any questions you have.